Okay, so chapter 4, second part. So position measure, they gave us, alright, to compare one data point to a set of data. So there are two position, okay, measures. The very first one is quartiles, and the other one is percentiles. So when we say position measures, we're talking about we're using the position in for a data set, okay, to compartmentalize that data set, okay, so that they're in each group that you can see clearly to understand what's going on with them. All right. So the standardized tests like SAT, ACT, and GRE, all right, graduate record examination that we have to take when we want to do the graduate school, and they all use the percentiles, okay? Not so much on Quartize, but the percentiles, and some of them they use that as well. And MCAT also LSAT. So after you finish one degree, you can go into professional study, or you can go into graduate study to become a professional, all right, to get into a professional career, not just a regular work, or to get into a graduate school to become philosopher. Okay, so all the professors are philosopher, and we study in our own field, and try to understand like what's going on in our own field. But after all, we're studying the us and everything we have around us and on the earth, okay, and a little bit beyond, of course. Now we can reach up to Mars right now. So anyways, it's all about studying where you are, studying you and your stuff around you and the environment, okay, outside, like that. Anyway, so we've heavily used the percentiles for the tests, okay, and all the stuff. Right, so let's go here, Quartize position measure. So first, you're gonna have a data. Split that data into, you're gonna have a data group. We're gonna split it into equally 25% each, okay, 4 groups. So split it into the same amount. So you have like approximately 25% in each group. And we call the very first one the first quartile, okay, and that's a 25, that's a 1-fold, okay, 1 by 4 data. It's gonna be in there. Q2 is the median because it is in the middle. We call it median, yeah. Again, median is the position. Okay, don't forget that. And then half of the data is going to lie from here to here, yeah. And 3/4 is going to be this guy right here. It's going to lie below, okay, the third quartile. Meaning like from here all the way to here, below. That's below. That's, okay, this is above. So from here to here, 50%. Okay, from here to here is 25. Yeah. And this guy is your median position M. Okay, so you got it. First quartile Q1, second quartile is Q2, and the third quartile is your Q3. Percentile. Percentile determined in the same manner, but this time we're going to break it into 100 parts. Yeah, not 4, but 100 parts for all of your data. So you have P1 all the way to P99, okay, on H. Okay, so the next one, probability. Well, probability is nothing but we're just thinking, okay, every possible thing that can happen in something, which is an event. We call it event. So event and then outcomes. We normally give this toss in the coin thing, but there are so many other examples as well, okay? So if you have the interest, you can read the probability book, textbook. and it's gonna blow your mind. Okay, so everything is probability in this world. So anyway, tossing two coins simultaneously tossing at the same time. Yeah, and we're using two coins, so we can draw this little coin right there, two coins, and we toss them. So possible things that can happen when you toss it. So you have to know what is a coin. So one coin has the surface, yeah, two surfaces. So we call the head and tail. Yes. Okay, here we go. We have some engraved on whatever prints on coin. So anyway, head and tail. So for each coin, we have two surfaces, head and then tail. And the other guy, another coin, second coin. This is the first coin, and this is your second coin. Also have head and then tail. So if you tossed it, what can happen? Okay, you have to think about it. You might get the first one head, the second one head. You might get the first one head, the second one tail. Okay, you might get the first one tail, and the second one head. You might get the first one tail, second one just tail. Okay, so possible things that can happen in this event, okay, we call that outcomes. Okay, so both coins shows no tail, which is this guy, outcome. One coin shows a tail. We have two outcomes here. Yeah, both show tails. We have one outcome. All tails, no head, or heads, no tail. One of them is a tail, therefore the other one is head. Yeah. So those are all possible outcomes. So every event, something that happened, scientists, what we do, research, okay, professors, what we do is to think every possible thing that can happen to an event without saying just one outcome. You have to come up with all possible outcomes. The same thing with COVID thing, right? Oh, COVID, we don't know. Is it man-made? Or is it a lab-made? Or is it naturally born? Everything is possible. So therefore you gotta put them in an outcome. Yes? What if this is naturally born? What are we gonna do? What if this is lab-made, meaning somebody cloning in PCR? What if this is, okay, man-made, again, cloning in the PCR and spreading intentionally? So you have to think about all outcomes, okay, all outcomes. So that is what we call probability. And you have percentages. In this case, we're going with the 1/3, yeah? 1/3 of the time, this can happen. Therefore, we want to guard or protect by this way. 1/3 of the time, this can happen. So therefore, the backup plan is this. 1/3 of the time, that can happen. Therefore, another backup plan is that. Okay, so that's all about research. So research is nothing but we have to think every possible outcome of whatever that is happening, whatever you're studying. Okay, so that you won't be biased, so that you won't overlook, so that you won't forget anything. Okay, so that you can come up with any kind of preventive measures, right, to do that. So anyway, we got it. Yep, the key point is right here. Every possible thing that can happen in an event got to be thought thoroughly out. Yeah. All right. Nature of probability, frequency. So now we have the outcome. Some of the outcomes, okay, they can be listed. So we're gonna list it in a table like this, so you can easily see them. Outcome 0 tay, 1 tay, and 2 tay. Nothing more than that can happen. You can also write head, head, head. Okay, doesn't really matter. It's the same for that event. And we're gonna write down it can happen 1 time, it can happen 5 times, and this can happen 4 times. Yeah. So event tossing the 2 coins. Toss the coins. This time, how many times we toss it? This is 9 and 10. We toss it 10 times. and we got it this. Yes, one of them is no tail, meaning like you're getting heads. You're getting one head and one tail. You're getting two tails 4 times. Okay, so here that's your data set. Yeah, so your trial is tossing coins 1 time. You repeat it in this example 10 times. Yeah, and we get that. Okay, so now let's go here, and that's the frequency. So now we're gonna bump our event into 10, from 10 to 100 trials. So we started out with 1 trial, we boosted up to 10 trials, and then now we're gonna do 100 trials. Yes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0 tail, we get 1 time, 2 times, 3, 1 time, 4 times, 2 times, 2 times, 5. Altogether, total 24 times we've got. 1 tail, we get 54 times. 2 tails, we get 22 times. Okay. So the total for 100 is distributed for these outcomes in this way. Now I use the word distributed, so your data are distributed in this way. 24, 54, and 22 out of 100. Yeah. So 0 tail outcomes 24 out of 100 trials, therefore 24% of 100 trial is with no tail. 54% of 100 trial is with 1 tail. We use 100 trial because we want to do it percentage. You know? 22% of 100 trial is with 2 tails. That's my data distribution. Okay, so the nature of probability, we did it with repeating the experiment 10 times. A single experiment is going to toss the coin 10 times. Okay, so here that's a single experiment. Since we're doing 100 trial, one single experiment has a 10 trials right there. So 5, 4, 9, 1 is 10. 5, 3, 8, 2 is 10. 6, 3, 9, 1 is 10, so and so. Yeah. You should be able to see the data very clearly like that. Okay, this is 550 is 10. This is 7 and that's 10. That's 10. That is 8 and this is 10. This is 7 and that is 10. Yeah. This is 8 and that's 10. That is 9 and this is 10. Yes. So this is 9 and that is 10 again. Yeah. So the same thing. 24. If you look at it, we already know that's 100. So practice your eye to be able to see the data in a data table. So therefore 10 experiment toss 10 times. So that's 100 trials. Yeah. Go on to the next one. Histogram is the starting point of the graph. We use the graph in order to see the data. Okay. So we draw the histogram. So we have 3 types, right, outcomes. One is a 0 tail, 1 tail, and 2 tail. We already know the percentages. This is 24%. Okay, and that's 54%. And this one is 22%. Okay, so now we see, oh, look at that. Just by looking at the data, you know that, okay, getting a 1 tail, that outcomes is the most. Yeah, followed by that and then this. And that's for the 100 rounds of your experiment. So the relative frequency, now we're going to use the word term frequency just a number of times. Yeah, might stabilize approximately 25%. Okay, so if you look at it, we're going to round it. That's 24, 24. So we're going to round 25%, 54%. We're going to round it to 50, and then we're going to round this to 25. So most of the time, if you increase the experiment up and down, okay, trial 100, 200, 300, 1000, whatever you do, we're going to get that ratio, approximate ratio, which is 1:2:1. Okay, there. So for this type of we have 2 surfaces and we're using a 2, okay, clients will give you that type of, okay, that type of data set, which comes with this type of ratio, okay. So that's what we call prediction. So if we have a similar, all right, event, I can tell you exactly, okay, which one to go just by knowing this ratio representing that type of set or that set of data, okay. And that many experiments you would do, then you will get this much of ratio, okay. So and that's how we do, and most of the things that we're doing in the world are based on the prediction on this, and you come to university to learn that, so you're ahead of other people, okay. Instead of doing blindly, you can calculate even in your life to be able to predict what you're trying to do, okay, because they're all data anyway. The entire world is made of mathematics, okay, all the shapes, we can draw it, and it doesn't change. Well, how many geometry do we have? It's very limited, right, in the world. So stat is a very powerful, all right, thing. I would say I don't want to say math, because the stat is not a math. It's just studying the data. Data come from all the events of the world, and if you master statistics, okay, you can really play with the outcomes of whatever events that you are dealing with in the world, including I'm trying to find a lottery ticket. Anyway, so lottery ticket is pretty easy, but then you have to have money in order for you to get more money, okay. And again, is another type of ratio. So some of the statistician will calculate that for you if you go and give money, and they will tell you the exact amount of lottery tickets that you have to buy in order to hit a particular winning, all right, ticket. So anyway, that's also calculatable. But then you have to have enough money to buy that amount of ticket, okay? And one of them is the winning ticket. So anyway, that's came from, again, stat, right? Studying the data grouping. Now let's continue to event. So probability is likelihood or chance or prospect. So probability of an event is the relative, again, of frequency. It's got to be relative, okay, because you have different outcomes stemming out from an event. So relative frequency with which an event will occur. So the total of the events is set again at 100%, all right, in statistic. So again, you already know it, okay, so don't try to get this by heart. What is the probability of an event? We're looking at the frequency, the number of the outcomes, right? And we have many different kinds of outcomes, and then we're looking at the frequency of each outcomes, and that's your probability. And it's usually set with 100%, yeah? All right, so now let's get into terms of how we write it mathematically. We write P with a little prime right there as your probability of an event right there. Then you have a number of that event divided by the total number. And I do not like this textbook. Okay, I've been complaining about, but because the textbook itself is okay, but the wording that the author makes sometimes a mistake, all right, in wording. So here it's supposed to be writing, okay, in the outcomes and the event, but then they use it very loosely, and you will get confusion, okay. So we know that there is an event and there is an outcome of that event, okay, and then we do the experiment. That is what you have to know, okay. And in the book, if you read it, you're going to see the terms are going back and forth, right, inconsistently. And I want you to pay attention for that, and this is one of them. And of course, we can change when we reference a textbook, then we can change the term of the author that they use, because it's against the rule. But then I will point out this is what's going on. So anyway, so right now an event is going to be n number of times the event happens, and then n total is the total times experiment was attempted. Okay, so here this is how we calculate by using the formula, right? So p prime event equal to n event divided by n total. Okay, since the probability is an event and we are dealing with the outcome and we're looking at the percentage of the outcome in that event, right? So we definitely have something called distribution, right? So we can see that, so how the numbers are distributed coming out from your frequency. Okay, frequency. Again, frequency meaning how many times the outcome happened. Like 0 day happened like 24 times. And then 1 day happens like 54 times out of 100 trial. Yeah, that's called the data distribution. So they are discrete, again, continuous, probability distribution. These are just a mathematical term. Okay, continuous and then discrete probability. I'll show you like what they are when you take a look at the graph. So in industrial metrology, it's just we're measuring that we're doing in industry. So we use these distribution in stat process control, which is SPC, to understand the process data. Okay, so probability distribution is stated in terms of, again, population. So the population is the set of all possible outcomes, all right, of an event. And then the sample is a subset of that population. Okay, we have a population, and a sample is a subset of that population. I'm going to erase this. Okay, so let's get into discrete probability distribution. So it is a sample of any set of possible outcomes, right, that have a unique result. So example, tossing 2 coins. Result, 1 of 3 outcomes. Okay, we already list outcomes, you should know by now. So the outcomes is all discrete. What is discrete? They are separate, right? We have 0 day, review, we have 1 day, and then we have 2 days. Okay, they're not continuous, they're standalone, and we call that discrete. Okay, separate results. And 1 of 2 discrete results, heads or tail. This is just showing you this main line, no head, 1 head. Sorry, this is 2 heads, 1 head, and no head. Okay, so discrete, we have binomial, okay, binomial distribution, and we have Poisson distribution. Again, we don't have to go into detail. This course, you're gonna take it only superficially, okay, for all of this distribution. If you know the name, well, okay. If you know the discrete as a separate results, you're okay for this course. Okay, binomial distribution. You only have to know the example of binomial equation. So units with defects, we usually write this way. So this little p is a fraction of the population that contains a defect. So we're studying the industrial, okay, inspection, and we take the sample out and then try to monitor the defect. So that's what we're doing here. So the fraction of the population that contains a defect, and we call that the sample population. P equal, okay, P D equal to X, meaning like D is a number of units with a defect, D for defect, and that's the data that we're studying. X meaning like just a data, okay? Data in this case that we're studying is a defect. And we use this, right, equation. It's kind of like a modified equation from the mathematics or statistic equation, and all we do is we put D, which is a defect, okay, for the data. So that's only modification that we use for the probability. The rest of them are the same. So n, okay, x, and then px, 1 minus p, to the power n minus x, and x is 0, 1, 2 all the way to n. Yeah. This equation is too close, so here you can just cut this out like that. So this n is your total sample from which d was taken. We'll continue the equation. P prime equal to defect divided by n, and your mean is mu equal to np. Okay, now instead of mean, sample mean, we also use little mu like that. Okay, and that is nothing but n times the probability. So this is showing you how to easily calculate mean in binomial distribution. The standard deviation, so instead of s, we're going to use sigma, yeah, this, and we can calculate this way for, again, binomial distribution of data, not regular data set, but a binomial distribution data. N times p, and then 1 minus p. Poisson, another distribution equation is going to change. Here you see the lambda, and thus the average number of defects per unit. In Poisson, mean is equal to your variance. Okay, that's because of the way or the shape of the distribution is. And again, you don't have to know everything. If you can just read it for one time, you're okay for this course. We're not stressing you for math at all. Okay, so fx equal to exponent power minus lambda, and then lambda power x divided by x. Okay, exclamation. That's just a mathematical function. Okay, and there's a way to calculate it. Again, you don't have to know this. This belongs to the Poisson distribution. Okay, when you get to graduate school, we'll teach you some more. Right now, just try to know, oh, the key point right here in Poisson mean is equal to variance, and if you know that, it's okay for here. So in Poisson distribution, I will use a factorial. So this exclamation mark right there here, if you want to review it, but then again, it's not necessary for all course, and that's called a factorial. Factorial. It's just a function. I mean, a calculation how to do this. But again, nobody is asking you how to do that, right? So you don't really have to know how to do it. But if some of you have already taken mathematics, then if I go like 4, if x is 4 or something, you would just go multiply 4 with 4 minus 1, okay, and then you go all the way down to 4 minus 2, and go 4 minus 3, and you stop for 4, yeah? So that's called the factorial. 4 minus 1, 4 minus 2, and 4 minus 3. We start with 4 minus 3, okay? So anyway, let's go. That's 1. 4 minus 3 is 1. And then you multiply all of that. And we call that factorial. Again, you don't have to do it here. I'm not going to ask you how to calculate it. That's 4. But you have to know this. For Poisson distribution, probability, mean is equal to variance. Alright, so continue the lambda prime, d by n, your defect divided by n. So lambda is the total number of defects found in the sample of n items. Alright, so here you have n items of sample, and then you're gonna find D. Okay, and that total number you can calculate this way. And then mean is equal to mu. Now in probability, mean is not x bar anymore. We use mu for probability, okay, problems, is equal to lambda. Now standard deviation is a sigma, is the square root of this guy, okay, which is lambda. And if you're interested, you can get into the meaning, all right? You can get into the meaning of this, but for this class you don't have to. So the meaning of Poisson distribution y mean is equal to this. Okay, that's because that's the total number of defects found in the sample of n items, and we're dealing with the defects. That's why it is equal. And standard deviation, okay, is going to be the number of defects found in the sample of n items. So therefore, we're taking a look at how many of them are deviated from that mean, okay, and that's what we call using the standard deviation. So if you have like mean this much, meaning like the total number of defects found in the sample of n items is this much, right? And you want to know the standard deviation, right? How far away it is from that mean. Okay, so you'll get your first sigma here. Okay, that's minus, and this is your plus 1. So if you have like the mean of finding the total number of defects found in the sample is that much, then you will get, okay, that many data right here, and you will compare that. Is it about the same as what it's supposed to be, or do we have more defects, okay, or less defects? So that's fewer defects. That's how we compare with the historic mean. And again, the average can be updated with every data set that we study. Okay, average is kind of like a standard that you compare to, and we always have the particular specification and a standard that you are monitoring your production. Okay, so if you say like I'm just going to have like a one, all right, defect out of a 100,000 products that I produce, and that's going to be my mean, then your standard deviation for any next batch of production got to be around there. And if not, it's so far away, you have to review your processes, okay, and correct it. There's definitely error. So that's what we're trying to do here. Okay, so continuous probability is the second one. Not a discrete, but it's a continuous. So in metrology, we work with continuous probability distribution all the time. So in SPC, so that's the industry, we're studying the process and monitoring the process by using stat. And this type of distribution, continuous, okay, probability distribution, we use it all the time. And we call that normal distribution because every time you take the data or whatever you're taking, and that data usually, okay, produce a graph like that. And every time you see this type of pattern, which looks like a little bell shape, we know that your data set is following the normal distribution. Okay, meaning like the data are distributed normally because it's producing, okay, the typical bell-shaped curve instead of something else like that. Okay, that's shape or exponent. Okay, and things like that. These are a little bit different distribution. So anyway, most of the time the data produce a bell-shaped curve. So let's see that in our next slide. So in inspection, normal distribution is used because most of the inspection data, they produce a graph like this. Okay? They produce a graph like that. So in equation, it looks like this. So we're dealing with k of x is just my data. That's a function. F means a function of x, so we're a process that we're studying, manufacturing. Okay, and 1 divided by 2 is square root of 2 pi sigma, and then e power minus 1 by 2, and then the whole thing. And that's for minus infinity, okay, all the way to positive infinity. Your data are going to be right in there. And that's just a normal typical way of writing what the data is. And then mu is your mean, and sigma is your standard deviation. And here, this is your normal distribution graph or curve. Looks like a little bell, okay? So we call that a bell-shaped curve. And the center is your mean, which is mu, okay? The standard deviation is all the data that's spread out from here all the way down. That way, this way. Central tendency. Central tendency is equal to mean. S is your standard deviation. We call that the dispersion. We already studied that. We talk about central tendency. In probability, we're talking about the mean. If we talk about the dispersion, we're talking about the standard deviation, and their corresponding symbols. So the calculation of population mean is the same as the calculation of sample mean, but they're not always equal, right? Calculation is the same, but they're not equal. The sample mean will approach the population mean when the sample size approaches the population. Meaning, like, if you have a population and you take the sample out of the population, okay, and your population have, let's say, 67, all right, stuff, and then you're sampling like 10 out of it, okay, the more you sample, and the more that number is closer to the population number, all right, that sample mean is going to approach the population mean. So we have sample mean is a little x bar, and the population mean is a x big, okay, big x bar. So the mean of this group, that is the mean of the sample group, okay? That's a little thing that you take out from there. So this number will approach that number when you sample more out of the population, okay? So we can be able to use this little mean for the sample and represent, okay, this data as that. If you have a certain, all right, number of sample that you take out from the population, so therefore we can safely use the mean of the sample, okay, as the mean of the population, meaning like we can use a sample mean as a representative, okay, representative of the population mean. So therefore we can use a sample to predict the population and apply, all right, our assumption of the sample on the population. So that's how we do, okay, stat, or use stat in order to predict. So by doing a little bit of work, we can be able to predict, okay, for the real one. All right, the next one is the central limit theorem. So this theory is developed, so it's telling you like every time you take the sample out of the population, okay, if you do like about 30 data, we take that as a really good approximation for the population. Okay, so if you study 30 out of whatever number of population you've got, and then you study this much of sample, we can be able to use this as a representative of that population. So approximation is pretty good. Okay, this is happening here, therefore, okay, therefore similar thing can happen to the population. So that's how we do the prediction. So therefore we use sample to calculate mean, right, and predict the population mean in the stat. Okay, and some people have issue linking the two. So they will have a sample mean right there, and then all of a sudden out of nowhere they have no idea how to link. So the link is you have to have, right, about 30 you have to do about 30 sample in order to represent the population, okay, by studying the sample. All right, and we call that the central limit theorem. All right, in normal distribution, we're going to do the same thing for population variance and standard deviation. So here's your familiar formula that I already showed you in the beginning, so I don't have to repeat this again. And this is your variance. That is your standard deviation. We're square rooting the variance right there, okay? Normal distribution, we use it all the time, very widely used, okay, for descriptive. Stat is nothing but organizing the data, okay? And then inferential stat, again, we're using inference by studying sample and talking about the population. Control charts, acceptance, sampling, systems, right? So these are everything that we study systematically, okay? Everything in order for you to get everything that you have at your home, all the products around you are produced by heavily using, okay, stat, because we have to study all the time for what we're doing so that we can consistently produce the same product with relatively good quality, okay? And some American companies are, I don't know what to say, but there is an issue, okay? And this is like people, I shouldn't say American, I should say just people are greedy, okay, very greedy. They want money, and that's all about in the world, because money is like the system of money is brainwashing everybody with the value, okay? Having paper money, and then you can go and get something by paying that, or credit card or whatever. So anyways, the money system that just destroyed quality, okay? So therefore, in production, instead of making like truly good product, we make just product that are usable. We change the word of the good product into usable product, and now the products are usable, but only okay up to a certain amount of time. So they put a time factor, okay, in the product. So therefore, in ancient time, if you make something, that stay like forever, yeah. Now it's like if you make something that should stay only in a particular time period, okay, that's design's been developed in the production that way. So therefore it will break, okay, it will just mess up, and it will just break down, and something is going to happen right in there. So they make the breakable product because of that time, okay, factor is completely implemented in the production. So ethically no good, but then they do it because they are hungry, okay, for money, and to buy houses and to put the things into the house and to have, okay, show around what you have or whatever. So that human ego that destroy a lot of the production system as well. So when you go into the management, you have to deal with the moral, okay, thing. Whether you're gonna treat the people and respect them and give them a good product, or you're just gonna make money by capitalizing them, by giving them what they want, which will break at a certain point so that they will buy from you again. So iPhone, the same thing. The beginning of iPhone was very good. You get a pretty good, quality product right there. But then they come to know that people want it. So start capitalizing by giving you different, right, updates, and different products that actually no good. Like how many people say iPhone camera making me look so ugly? They made it that way in order to protect also the regular camera, right? And this is like the thing that management also facing. Okay, the whole thing, like um professors also in it, right? We don't like it, but it's the way the world is going in that direction. Doesn't make you feel good. And people are just making the product to get money, and the greed is incredibly high. Okay, greed is high. So they put a time factor in it and capitalize your desire. Okay, so let's go the marketing survey and then studying what do you want? What is it that you want? You want this one. I'm going to give you just a little bit of that so that you will buy some more. Okay, so those things are like based on education, by the way. But then we didn't teach you to do that. Okay, we teach you to develop the good product. But then the ethics is that's something else. Okay, that's come with the evil part of human ego and also human nature, the evil part of human nature. You have a good part and you have an evil part and bad part. That's all mixed in human nature. So anyway, so even though we talked about jobs and everything, so when you get into big company, that's also one of my challenges that I face in my life, that I come to know that I can't do it. Okay, I'm more of a, I think morally, I lean towards the morally correct, which is against the money making thing. Okay, and it's pretty like stretching you, like stretching you mentally. Okay, right in there. So anyway, I want to tell you that okay, after you finish your school and go to work, or maybe you already work and already know about that. I don't even have to tell you that. Anyways, those are the things that you will face. Okay, getting a job is easy, but doing the job is really hard. It's a whole different game. And whether you like it or not, okay, it depends on the nature of you and the nature of your job. So you have to play within these boundaries. Okay, so let's go back to the normal distribution. So it's widely used, okay, for descriptive stat, and we already talked about inferential control charts, except in sampling system, we heavily use it, okay. Mean and the central tendency is nothing but the 50% of data points, right? It's going to lie on each side of the mean, so that way. And that's pretty, we call that the normal distribution, okay, 50 here and then 50 there. All right, so let's erase this board and go on to the next one. Okay, so let's continue the normal distribution right here. So get into standard deviation. Usually you will see plus or minus 1. Again, that's not mathematics, that's a direction. Okay, on this direction and that direction. So from the mean will contain 68. Okay, from here to here, we're always looking at that way. Okay, so your data are on this side, also on that side. Okay, don't think this in a mathematic way. Your mind is going to go crazy again. So 68%, 94%, and then 99% are going to be distributed, okay, away from the mean that way, spread out. 50% of the data and then 50% of the data on that side. So plus or minus 2 standard deviation from the mean will contain 94.5% of the population. So this one, okay. So here is our cutoff. There's 2 standard deviations away from the mean right there. So that's a 3 standard deviation, meaning will contain 99.7% of the population. So the distribution is going to go infinity to this side and then to that side. Okay. Now we're going all the way to 6 sigma. So that's another greed, okay, greed of the people right there. So anyway, 6 sigma is a go stretch out to the 6 standard deviation, okay. And it will contain almost everything, meaning that we're not letting we eliminating the defect by playing with the specification, by designing, right, designing the production or the designing the process. Okay, so this is the last one, is a sample and sample variability. So this section for your course, they have eliminated, so you don't have to study that. But they are MCQs, all right, coming on just a few questions. So for this, you will have to just research by yourself, either Google or you can read it in the textbook. But again, by department wise, is we're not getting into this because that's mathematics, okay? And instead, you have to take another course under SPC. It's a graduate course. So anyway, so we're gonna stop right here, and that's it for today. Yeah. Okay.